Good morning and welcome to chapter 15 basically for this class. Today is October 20th. We're slightly basically on the other side now of the mid-semester. So we are toward the second part, and we should have an exam coming soon, probably in early November. It should be on Canvas. When is that supposed to be? And it's going to cover the chapters basically that we started already on the up to chapter 19, I believe. Okay. So this is in terms of everything. I know I did not assign things last week because of the fact that we had an exam, but we look forward for this week. I know chapter 16 is not ready yet. We have to clean it a little bit and make it right for Canvas before I upload it. And with it, there will be assignments for the previous chapter and this one. Okay, so this is in terms of everything. If you guys don't have any questions, so we're going to dive in quickly into this chapter. This chapter deals mainly with chemical bonding. So we're doing a little bit of general of everything. So we're introducing a lot of concepts in here with not a lot of depth in any of them, but that's fine because we would want to have an understanding on how everything works in terms of general principles, basically. So today is chapter 15, and namely how atoms bond. Okay, and molecules also attract one another. So this is going to focus more on the basically how atoms bond to make chemical bonding basically and form molecules. But we're going to probably cover a little bit of the second part in this chapter. Okay. So again, this is the ideas of this chapter. First of all, the electron dot structure. This is representation basically of the outer electrons inside of the atom, so that to make them ready for any kind of chemical bonding later on to form pairs together or with other basically atoms. So this is a representation using that basically the dots. Okay. And for that, we're going to focus mainly on the shell structure for the atoms. And again, that's a model. It's not really how the atoms actually really look like. I mean, they're a little bit more complicated, but that gives me an idea into, okay, the farthest most from the nucleus, because they will be available for any kind of interactions with other atoms. So that's basically how that is. All of these interactions, they're electrical in nature. Okay, so the electrical forces, the ones that cause the bonding between the atoms to form different molecules, and actually the molecules also between one another, either directly or indirectly. Okay, either with the fact that they have positive charges interacting with negative charges to form chemical bonding, or an induced charges. Although the first one, for example, is neutral, but you induce by moving the charges in one way or the other and form, in a sense, bonding with the portion that has been induced in the opposite sign. So that's all of it is electrical, basically, connections. Again, the formation of ions, basically the fact that one atom would lose an electron and becomes positively charged, then the other one gaining an electron becomes negatively charged, so it become basically ions. And this ionic basically structure is not only valid for the atoms, actually it's also for the molecules themselves. So you could have molecules basically behaving as ions by losing one of their hydrogens or gaining an extra one, or so on and so forth. We'll talk about the ionic bonding. This is basically one of the things that I already mentioned, the fact that one atom loses, for example, an electron, another one gains one, and now you have a positively charged ion and a negatively charged ion next to one another. So they will become electrically attracted to one another, and that forms the chemical bond between them. Metallic bonding is a little bit different in a sense. In metals, for example, iron, or do I have any pieces? Yeah, I have. This is a piece of iron. Actually, it's a magnet also. In this case, what's going on actually is that it's a little bit different. You have the atoms that are positively charged, of course, if they lose electrons, and the electrons in metals, they're free to move. So now you have a bunch of electrons basically floating around, forming what looks like a fluid, basically. And those electrons, they bond the atoms together. Now you have one atom that is now lost did not really lose because at any point it's still neutral because of the floating electrons, and this one also next to it. Now, these two, they are held in place with this glue, if you wish, if you can think of it. That's the metallic bonding. Covalent bonding is a different one, where two atoms, typically of the same type, for example, oxygen and oxygen, or nitrogen and nitrogen, what they do in this case, they are neutral, both of them. They take the outer electrons that they have available for chemical reactions, and they share them and they hold on to them. Okay, so it's a little bit different. So in a sense, they did not lose their electrons like the ionic bonding, but this is they share their own electrons and now they become bound together. This is, for example, for the case of oxygen, O2. Okay. Polar covalent bonding, now you're talking about different kind of interactions in which you have an imbalance. You have one atom that has a lot of positive protons inside of its nucleus because it's heavier, and you have a lighter atom that has less positive electrons, positive protons inside its nucleus. When they enter into connection, the electrons move closer toward the positively charged nucleus than they are on the other side. Now, leaving what looks like a depletion of charge on one side, and so this will be positive because it lost an electron. This now it has moved the electron closer to it, so it looks like it has gained a charge. Okay, this is not necessarily an exact electron that has moved because yes, the electron has moved, but did not move completely. Okay, so it's not an ionic structure. Okay, in this case, what you have a dipole, an electrical dipole, actually. You have a positive charge on one side and a negative charge on the other side, and both charges are equal, and you have what is called an electrical dipole. Okay. This dipole now interacts with another dipole in a sense that if this is negative positive and finds another one that is negative positive, so they connect to one another. Okay. This is the case of water, for example. Okay. And then you have another kind of dipolar basically interactions where a dipole induces a dipole in another atom that is otherwise neutral. Okay. For example, to go back to the example of oxygen or the example of nitrogen and fluorine, both of them have the same power. So the electrons, they sit right smack in the middle. So they are not going to have any dipolar structure. In other words, there is no charge that moves one way or the other in a sense that both of them have zero charge actually in this case. But when an induced dipole happens, in this case, a charge moves actually to one side than the other one, and now you have what effectively looks like a dipolar dipole in this case, and you will have a dipolar interaction. The trouble with that is sometimes this is not a permanent configuration; it can be temporary. Okay, so and that is basically what we talk about when we talk about the molecular polarity. Okay, so it has a lot of interesting applications. Of course, for example, in case of drugs, you would want to have uh, uh, um, um, molecules that carry the drug to a specific location. In the case of soap, in the case of all kinds of applications, and it explains also some other phenomenon why, for example, certain molecules at room temperature are liquid versus why others are gases, albeit it's not just a matter of mass. Because, for example, in the case, and it's an example in here of carbon dioxide, CO2, it's a lot heavier than H2O. Okay, H2O has only one oxygen and two hydrogen atoms, and this is the hydrogen atom is the lightest in terms of the mass, and oxygen, the carbon dioxide has actually two oxygens, relatively speaking, so plus carbon. Okay, so it should be heavier. Whereas in room temperature, carbon dioxide actually is gas and water is not. Okay, so this is some of the things that we try to understand from this chapter. Okay, and the discussion is related to the last point, exactly to this point that I mentioned in here, into why, albeit CO2 is heavier than water. Water at room temperature is liquid. It looks like it's sitting still, and the carbon dioxide is gas. Okay, So basically, so what Sarah is asking is to put the question in here. So the question is why CO2 at room temperature, I don't know, yeah, I spelled it correctly, temperature is gas, whereas water is liquid, albeit CO2 is more massive, heavier actually in this case because of force of gravity. Let's put massive in this case. Let's put just focus on the mass in here, more massive than water. Does this make sense to you, Sarah, and everybody else? I don't understand, Sarah. Is that Spanish? Or are you missing the Y? Okay. Okay, so let's continue the discussion. Okay, okay, that's fine. Okay, so I thought so too. Let's continue this discussion in here. So again, I mentioned the dot structure. Basically, we talked about the entire chapter. If you don't, I mean, we've basically the entire everything that we're going to be covering in here. Although we should really look for that answer somewhere, we have to really be accurate into why that is. Okay. So atoms bond together through their electrons. That is really the key for all of the interactions. So it's an electrostatic. All chemistry is based on electricity. Okay. All chemistry is based on the forces of Coulomb, namely two charges attract one another proportionally to their charge. So if you have charge, you play the game. If you don't have a charge, you're out of this game. So electrons have charges, protons do not. Protons, they're way inside the nucleus, so they cannot do anything. They don't participate in this game. So the only things in town are actually the electrons, and the electrons can move one way or the other, or can be shared. So that's basically all of chemistry. All of chemistry can be summarized in this basically statement, the fact that electrons are lighter and not tied into the nucleus. Therefore, they interact electrostatically via electricity, basically. And electricity states that the force is proportional to the charge. It's, of course, inversely proportional to the distance, but that's another issue. The charge. You have a charge, you play it. You don't have a charge, you stay out. Okay, so that's basically in a nutshell what the whole process is. To learn about bonding, therefore, we need to know about how the electrons within an atom are organized, okay? So that is basically the key thing. So we had to really understand that in order to really see how the bonding happens, okay? So in terms of energy, in terms of interactions, and even in terms of distance overall from the atom, they look like in some sort of levels called shells in this structure. So we put them in a shell like the onions, basically shell, and each shell contains specific number of electrons. Okay, so the innermost shell has to be filled first. Then, when it's full, then you go to the next one, and then when it's full, you go to the next one, and so on and so forth. That's how you basically move through the periodic table. That's how you go from one atom to the next, to the next, to the next. That's what forms basically the different groups in the periodic table. Okay. Now, when we move from basically how many electrons at the end are available at the end, that is how we move in the periods in terms of the periodic table. So that's basically how we organize this ones in here. And again, we talked about this one. Why you really have to have two is because you have to fill the entire energy level in there, and there is a principle actually of exclusion of Mr. Pauli that prohibits that two electrons would occupy the same quantum state. So at the end, both of them will have at least one thing that is different, namely at the end, at least the spin. Okay. So again, it looks like this is, again, I'm just talking about the fact that this is a conceptual idea, not really the you should not look at the atom some sort of an onion. That is not correct. I mean, at least picture, because the whole atom is really not a classical object to talk about it in that sense. So it helps us to understand how the electrons behave and interact. Again, this is basically, we're talking about in here in the last column for the periodic table, the inert gases. For the first one, which is the helium. In this case, helium, you have two electrons at the end. This is the neutral helium, not the alpha particle. Okay. So, and that is full. So the last shell is completely full. The same thing also is true for neon. For neon, the second shell is full. So for all of these inert gases, they're full, and they go back into the periodic the shell structure, and you will see all of these numbers are filled up to the maximum, and that's why actually they are very, very hard to have them chemically active. That's why we call them inert, because of the fact that they don't interact as much with other in terms of chemistry, because they don't have an electron, spare electron, to integrate, to participate in any kind of interaction with other atoms, and they don't have an available space for anything. So all spaces are occupied up to the maximum. Okay, so the first shell is full, and that's it for helium. Technically, you cannot do anything with the helium in terms of interactions. Okay, same thing with neon. The last shell, which is supposed to have 8, and all 8 are full, so it doesn't interact with the with anything. And last one also in here in this example, argon. So if you follow the entire list, you will find them full. So most of the time when we talk about chemistry, chemical interactions, we focus on other elements other than the last basically group in here. So valence electrons are electrons in the outermost shell of an atom. These are the ones that participate in chemical bonding. So that's why we don't have any in here. Okay, they're all basically bound in here. Okay, so that is the outermost electrons that can be basically participate in the in chemical bonding, and they are represented with dots. So that's basically how we can see the chemical properties of different elements in here. For example, in the case of chlorine, I have 1 ampere. So chlorine technically can give that electron or take another electron. Okay, in this case, it has affinity for electrons, so it's going to take 1 actually. Carbon in this case has 4 ampere, so carbon in this case can participate. This other three, they are already paired, so you cannot do anything with them. It's similar, the other 3 are similar to this 2 for helium, and to this 8 for neon, and the last 8 for argon. They're all paired. They're already basically bound together, so they cannot be given or take anything out of them to them. But in this case, for the case of chlorine, you have 1. In the case of carbon, actually, you have 4. Okay, so there is a rule actually in quantum mechanics, and actually in that basically prohibits that this 2. Once you have 4 in here, first you have 1, then 1 by itself, and then by the end, when the 5th electron comes in, that is when the pairing starts to happen. Okay, like in this case, for example, I have 7, so I paired the 2 and the 2 and the 2. Now I have 6, and I have 1 available. Okay, krypton, for example, has all of its 8 atoms in this case fell to the last. Albeit now, if you look at the periodic table, krypton comes after argon, and after argon, if you look at this number, actually it's 18. So in this case, we represent just the last 8. That's a representation, that's all, in terms of the dot structure in here. So this is the model for the dot structure in terms of trying to show where the valence electrons are. So basically, we see them. Okay, so this is a periodic table now in terms of this dot structure. If you look, for example, the first column in here, the first group in this case, they all have 1 electron that can interact with anything on the other, with any basically in any chemical bonding. Now, beryllium, magnesium, calcium, and everybody else on this second group has 2 actually, and you move on to the third column, 13th column in this case. There is, I'm sorry, and then the carbon, and then you come into, for example, fluorine and chlorine, bromine, you will see that they have room for one taking another electron. So technically, I can form, for example, sodium and chlorine, and that is actually what salt is. Sodium can give, for example, one of its electrons, and chlorine will take it, and chlorine now will become negatively charged, whereas the sodium will become positively charged, and now I have two ions. Okay, and that is basically the principle of how salt is formed. Okay. And the same thing with all of the other salts that technically can form, for example, between any of these metals on this side and any of these elements on the other side. Okay. So that's the question. Sodium, atomic number 11, has only one valence electron. Exactly one. Okay. Just like lithium, just like potassium, and all of the other elements in there. Okay. Now the question is, upon losing this electron, what other atom in the periodic table does the sodium thus resemble? Okay, so it has 11. It lost 1. So it must look like 12 or 3 or itself. It has lost an electron. So if I go back now into this structure, the shell structure, where is the first one? So it has 2 plus 8, that's 10, plus 1 in this shell. Okay, so it had 11 and it lost it. So now it should have 2 plus 8, and 2 plus 8 should put it in the periodic table similar to this guy. Yes or no? I have 2 in here and 8 in here. So it's going to be similar to, because the last shell now is gone. The last electron is gone. Does this make sense to you guys? Yes?
Yes.
Okay, very good. So basically, once we have this image in our head, basically the shell structure. Did you say no? Okay.
Sorry, I was trying to mute.
Okay. So so once we have the shell structure in mind, basically, then it explains a lot in terms of basically what's going on, especially in terms of these ions and so on and so forth. So let's go back into the question. Where is it? So the correct answer is 10. Okay. So basically you lose 1, and now the shell structure, I know mathematically 11 minus 1 is 10, and that's the correct answer, but in terms of the shell structure, it looks like now it's neon, except that don't forget that you have 11 protons underneath inside the nucleus, so it's positively charged now. Okay. So now it's a positively charged once it loses that extra electron that was neutralizing the other proton inside the nucleus. Okay. And so here is the structure. Basically, it lost that electron. Now, in terms of the shell structure, it looks just like the neon. Okay. So the vacant shell now is empty. Okay. There is nothing in there. But of course, as I said before, because you still have 11 protons in the nucleus, now you have a positively charged, and it's a positively charged by 1 exactly. If you take let's look at the periodic table in here. So this is neon. It has 10 altogether. Fluorine has 9. Okay. So in this case, it has the potential of gaining 1. Okay. So if it does gain 1, it's going to have 10. It has moved up actually to also the neon. I mean to yes, it moved up to the neon. Okay. So if it gains 1. So either the sodium, by losing an electron, would behave like neon, or the fluorine in this case gains 1, and it's also going to behave like neon. At the end, the outer shell will be full. Okay, so that's the in terms of the ions and how they move one way or the other. Okay. Okay, molecular ions is also similar in a sense, but in this case, either you gain a hydrogen atom, ion or lose one. At the end, you will basically, as a molecule, you will have actually a charge in this case also. So in the case, for example, of water gaining an extra ion, an extra basically hydrogen ion. So in this case, it's going to look like this. So you'll have 3 hydrogen atoms connected to a single oxygen. Remember, oxygen is already neutralized by the presence of the other 2 hydrogen atoms. Chemically speaking, it also now has no room for. But when it bonds together with another hydrogen in this case, then in this case, I will have a positively charged molecule in this case. So it's not only for the fact that you can also do it for atoms, but also for molecules too. Now, all of this in terms of charges is again leading to a very important concept, and that is the fact that chemical bonding is all dependent on how these charges are moving one way or the other. Okay. So ionic bonds are the bonds that where you have an ion and an ion, and now they are electrically basically connected to one another. So an electrostatic force. This is an example. Okay, sodium lost an electron, now it's positively charged. Fluorine gained one, and it's negatively charged. Now the electrostatic force will bring them together, and until basically they form the bond. Okay, so now you have an ion and an ion. One of them is positive, the other one is negative, and if they maintain their charges in this case, so they're going to enter in a chemical reaction. And chemical bonding. And this chemical bonding in this case is 1-to-1. Okay, you have one electron, one positively charged in here, with one negatively charged in here, and they will hold to one another. Okay, here is an example where this 1-to-1 is not correct. Okay, I have 3 positively basically charged aluminum and 2 negatively charged oxygen. Okay, and I want to form the oxide of aluminum in this case. How am I going to do it? If I bring them together, just like this, I will still have one positively charged, the whole thing will be positively charged. So that is not a neutral. I need to neutralize both of them. So if I multiply this by 1 and multiply this by 1 and add them together, I have positive 3 minus 2, so it's still positive 1. So this is not a valid bonding in this case. Do you guys understand? A is not correct. How about if I bring 3 aluminum and 2 oxygen? 3 times 3 is positive 9. 2 times 2 is a negative 4. Positive 9 minus 4, that's still positive 5. So this is not actually correct bonding, because the molecule itself is still charged, negative or positive. Let's think about this one. I have 6 aluminum and 6 oxygen. 6 times 3 is 18. 6 times 2 is a negative 12, but still positively charged molecule. How about this one, C? 2 times 3, that's positive 6. 3 times negative 2, that's negative 6. Positive 6 minus 6, this is a neutral molecule. This is a stable molecule. This is basically now chemically bound via ions. So I bring 2 ions of aluminum and 3 ions of oxygen, in this case negatively charged, that gained 2 electrons basically. This one lost 3 electrons. So now you put them together, and now they're going to stick to one another, and it's going to be bound, and that's going to be a stable molecule. Okay, so the correct answer to this one is Al2O3. Okay, here is another example. Okay, this looks correct, all 3 of them. Okay, you have magnesium that has lost 2 electrons, and and oxygen that has gained 2. And if you add the numbers, 2 minus 2 is 0, or 4 minus 4 is 0, or 8 minus 8 is 0. So the correct in this case is the most stable is the first one in this case, because that's all you need. Okay, that's it. It has formed in this case, MgO. Because it's a 1-to-1 correspondence in this case, and the least common common multiplier. In this case, also the same thing, the least common, because there is another possibility in here. How about Al4O6? That's still correct. Okay. So if I have 4 times 3, that's 12. 6 times 2, that's 12. But we need the least common multiple of this two numbers, and the least one is in this case 6. 3 times 2 is 6. That's the least common multiple of the two. Okay. Same thing in this case. It's a 1 to 1, so it's 1. So the metallic bonding, I already talked about the fact that in the case of metals, the electrons, they're loosely bound and they're actually they belong to the entire community of the atoms. So it's like they are all shared. And that sharing, that kind of fluid basically of electrons is what keeps the metal basically together, what holds it together, okay? Most metals, when they occur in nature, they don't occur really in pure state. We really have to treat them in order to bring them with higher concentration of their metals. I think there is only a couple of exceptions. I think one of them is gold, okay, that you can find it in nature actually in pure form. So that is the so this weak attraction basically of freely basically moving electrons, the cloud of electrons, is the one that provides the bonding in this case. Of course, the fact that you have those available electrons, that accounts for a lot of the properties that makes the metals useful. One of them is the conductivity of both heat and electricity. The other one is that you can shape them basically easier. And they have a lot of properties that are very useful, and that's why they are used on a daily basis in everywhere, not just in the kitchen, but also in the industry and a lot of places. So that's why they're heavily sought. I mean, all cars, if you think about them, they're really based on metals. Alloys are a mixture of different basically metals. So it's the same thing in this case in a sense. So you can have that chemical bonding using the community of electrons of two different metals combined together. But again, they're not necessarily they're not connected to one another. The type of alloy that you're going to have depends on the concentration of the different metals that you have. What you want to achieve in terms of properties, physical properties, it depends only on the proportion basically of the different components of an alloy. Okay. Which brings me to another kind of bonding, which is the covalent bonding. And in this case, basically two atoms, like Kevin here in this case, fluorine, they share, they bond together via the sharing of their common electrons. So neither one will take it. Okay, so basically they put it between them and they start bonding. So remember, we have room for one more electron in this flow, other one. So this gives one of its, the other one gives one of its, and they actually hold on together to it. So it's not really, nobody takes anything from the other. So now in this case, I have F2, which is in this case the fluorine molecule. Okay. This is true also for the oxygen bonding, for the oxygen, and so on and so forth. Usually it's the same type of molecules that form this kind of bonding. We use representatively, I mean, so instead of the for the ionic bonding where we actually have dots moving around and so on and so forth, for this one we use actually straight line, just to indicate that they are not actually, they did not displace from one atom to the other. Okay, so when you put them together, this is basically how this looks like. Obviously, if I have, like in the case of oxygen, more than one electron that it can enter into, so in this case, you can have two covalent bonding in this case, because it can bond with one electron with the hydrogen and the other one with hydrogen, forming the H2O in this case. For the case of nitrogen, I have three actually. I can potentially do three covalent bondings because I have three free electrons. So three covalent electrons, three valent electrons, so they can enter into covalent basically bonding. And since I can do that, now ammonia, that's how it's formed, okay? You have three hydrogen atoms forming together, bonding together with an atom of nitrogen. And the same thing, for example, for methane, the one that we use for household daily experience to burn it, okay? So again, you have the carbon in this case has 4 electrons available for covalent bonding. The hydrogen has 1, so you can bring technically 4 hydrogen atoms, connect them in this way with the carbon. Now, this is only with basically paired electrons. For example, in the case of CO2, you can have 2. In the case of O2, actually, you have in this case 2 covalent basically electrons. They move together and now they are shared in a covalent bonding. Same thing with the CO2 in this case, or N2. Okay, N2, you actually have 3 of them. In the case of hydrogen, for example, the electrons, when they're connected together, they're actually in the middle. And in this case, the atom is non-polar because in this case, the molecule is non-polar because in this case, it does not have a charge moving one way or the other. In other words, these electrons, they don't tilt to one side or the other. Both of them have the same power. Both of them have the same affinity for their electrons. Basically, they don't move the electrons one way or the other. However, in the case, for example, of hydrogen fluorine, in this case, you have more positive electrons inside of the atom of fluorine. So the electron in this case, albeit it's shared, but it's actually closer to the fluorine than that is on in the hydrogen, because the hydrogen has only 1 proton in the atom. So the electron in this case moves closer toward the fluorine. Okay. And in this case, you actually have a dipole because you have what looks like a positive charge near the hydrogen and a negative charge near the fluorine. Okay, so it looks like you have you have a structure where the 2 charges have been separated. Okay, and they're equal amounts of charge because as the electron moves slightly, in this case, the distance between the where it left the empty space, if you wish, where it became positive because you have a proton still left in that place, and now where it has moved slightly, where you still have now the atom of fluorine itself is supposed to be neutral, but an electron came closer to it, so now it looks like you have a dipole, and a dipole by definition is 2 charges that are equal in magnitude, separated by a distance between them. Okay, so that's what the electrical dipole is. Electrical dipole have interesting interactions. Okay, one of them is you put it in an electric field is going to spin, rotate. Okay, and the electronegativity actually measured the affinity for those electrons. How much an atom is more likely to attract towards it an electron than another one. So that's basically the power of pulling electrons towards it. And in the periodic table, it's higher toward the right. When we talk about that, we don't really include this one, the inert gases. You don't talk about them, okay? The atoms on this side, it's high, versus the atoms on this side, it's low. So when you're looking at you're trying to understand, can I have a polar structure? Can I have a dipole basically forming in this case? Yes, if you have one, for example, coming from this side, another one coming from this side, and as you move higher and lower, depending, you're going to have an affinity for the electrons. So this is basically some of the properties in terms of the atoms and how they form, or whether or not they can form basically polar structures or not. This plays a major role, for example, in the case of soap. How does soap sticks to dirt and takes from your hand to with the water that so it acts as a facilitator in this case. So again, in terms of representations, we're not done with the discussion yet. Somebody's already commenting on it. Okay. So there will be potentially more questions. Did anybody put a comment already? course, you can communicate privately if you don't want to.
I accidentally did it.
Okay. Okay. Because my watch was telling me that. Anyway. So basically, this is the representation for the dipole in this case. As you can clearly see, in the case of sodium fluoride, this is a strong dipole in the sense that the fluorine in this case has higher affinity, and it attracts towards it the electrons closer, and it looks like you have a very strong dipole. Whereas, for example, in the hydrogen fluoride, it's kind of a little bit less because of the strength of it is a little bit not that strong. And in the case of fluorine, there is none. So we're not going to represent it. So that's a representation, if you wish, for the dipolar structure in this case. Again, this is the question of the day. Okay. So which is heavier? Of course, CO2 is definitely heavier than H2O. Count, for example, CO2 is 12, oxygen is 16. 16 times 2 is 32, plus 12, it's 44 atomic mass units, AMUs, okay? Whereas in the case of H2O, you have hydrogen is 1 times 2, you have 2 of them, so you have 2, plus 16, that's 18. 18 AMUs, or 18 times the mass of a single proton, which is something like, 10 to the negative 27 kilograms. That's if you're talking about an proton. Then you multiply it by 18. 18 is definitely less than half of 44. So CO2 is much, much heavier, more than twice the water in terms of masses, at least. So which one is heavier? Definitely carbon dioxide is heavier than water, okay? So that's the correct answer to this question. So there is no question about it. And so why does it behave? So in this case, water is heavier. Doesn't make sense, okay? It looks like because it's liquid, whereas the other one is gas. Usually our intuition tells us that the gas must be lighter than a fluid, must be lighter than a liquid, which must be lighter than a solid. Solid typically for us has more mass in it, more weight in it than that of the liquid, than that of the gas. But that's not the case actually. It's the other way around in this case, and it's a practical example in this case that the CO2 is more than twice heavier than that of the water, yet the water sticks. And the reason why, it's because the H2O actually has this dipolar structure. In a sense, what you have the two hydrogen atoms having their electron move closer to where the oxygen atom is. So now you have a positively charged hydrogen side and a negatively charged oxygen side, and all of it looks like a dipole. Now, if you happen to have another water molecule next to it, that is going to be, the hydrogen is going to be attracted toward the negative, basically, side of the oxygen, and you have basically formed another kind of bonding. The molecule itself is stable. H2O is already neutral, but it has this dipolar structure. Now you have a dipole and a dipole, two different molecules of water can interact and basically bond together. Whereas in the case of CO2, that is, what is the structure for CO2? Here. In this case, it does not have a dipolar structure, okay? So now, yes, the CO2 is heavier and they're neutral, it's neutral, but next to another CO2 also it's neutral, and there is no dipolar structure in here to allow for CO2 and another CO2 to bond together. That's why all you need is temperature at room temperature for the CO2 to be in gas form. As a matter of fact, you can liquefy it, but not for temperature much lower than 0 degrees Celsius. So in other words, you need lower temperature before it becomes liquid. So that is, or different pressures in order to produce the liquid CO2. So that is why, in this case, so that's the answer to the prompt today, why CO2 in room temperature is gas, whereas the H2O is water. So all you need is very little energy compared to that of the water to make it into a gas form than in the case of the water, because in the case of the water, you really have to break. You have to spend more energy to break that bonding between dipole and dipole. Does this make sense to you guys in terms of the answer? Yes. Because CO2 is non-dipolar, whereas H2O is dipolar. So there is more room for interactions between the water molecules to form bonds, and you need more energy to break them, and make them into gas. You need to reach 100 degrees Celsius before it becomes gas, because it vaporizes basically. Yes?
Got it.
Okay, very good. Yes, Masada, that's correct. That's the question for today, and that's the answer for it. Does it make sense to you, Masada? Okay, very good. So again, we were talking about the fact that in the case of the CO2, it doesn't have a dipolar structure, okay? Whereas in the case of the water, it does, okay? Whereas in the case of the water, I have a positive, basically what looks like a positive charge has shifted because there is a depletion of electrons. The electrons, they shift closer to the heavier mass, which is in this case the heavier, because they have more protons, if you wish, next to the oxygen. So it has a great affinity for electrons than that of the hydrogen. So it's going to bring them closer to it. And now it looks like I have a negative charge in this case. This delta is really how strong the charge is. So this is not two electrons, but it's a partial. So it's not 3.2 times 10 to the negative, say, 19 coulombs. That's basically the point I'm trying to say in here. But it's a value nonetheless. Okay, it's not zero, and like the previous case for CO2, which is truly zero. Okay. Uh, so in this case, I have a dipole. Now, if I have two of this, they can bond together. So I have a water molecule in here, in this case, being attracted, the positive side attracted to the negative side, in a dipolar interactions, and in here I have a positive and a negative. So they become bound together via these interactions, okay? And now I have the whole thing is what forms the bonding in case of the water for using this molecular polarity, okay? So, which brings me to the second part of this question, which is water has such a relatively high boiling point because it boils at 100 degrees Celsius, is because it's a heavy substance? Is that the cause? We saw that it's not as heavy as CO2. Okay, we can calculate them actually. Is it because it's transparent and so that heat passes right through it? That's a funny answer. Okay. As a matter of fact, CO2 is also transparent. And it's because it contains 3 atoms per molecule. So it's actually CO2. Okay. Or is it because molecules are so sticky? If you have downloaded this presentation, you know what the correct answer to it is. Okay, Manuel thinks D. Everybody thinks D because it's actually part of the PowerPoint. But the question now, the second question of the day is why? So we already have one question. So the second question, which is immediately related to this question in the PowerPoints, is that, and you guys entered correctly, which is molecules are so sticky. Why are they so sticky? Why the molecules? Okay, let's answer Sarah's earlier question, which says that put the questions on the chat, please. Okay, it's very good. So why are the water molecules so sticky? Does this make sense to you, Sarah? Everybody else? And we need an answer to it quickly. So why are they? Because I need somebody to guess something. This is not a democracy, guys. So everybody has to say something. You are required to vote in this case. Kind of. It's the topic actually. Kind of, Emmanuel. You're almost there. Hydrogen atoms which are arranged on one side of the molecule. It has a name, Sherry. You're right, but it has a name. I'm looking for a word in here. I mean, you described the situation. Actually, it goes for everybody too. It's not Sherry who basically stated it this way. What Sherry is saying is that the I know people who are not live with us, they don't see what people are writing in here. The extraordinary thickness of water is due to the two hydrogen atoms which are arranged on one side of the molecule. There is a word that I'm looking for, Sarah, too. And the word is this one. Let me show you. It's actually this one. Because of the polarity of water. Do you see that, Masada, and everybody else? Okay, very good. So that's the word I'm looking for, okay? So if somebody asks you, let's say, for example, you're going up and on an elevator and somebody, hey, what's wrong with water? Why is it so sticky? That is the word that you're going to use it for them, okay? You don't need to give them a big description because of the molecular polarity of water, okay? That's it. You're good. If they want to know more about it, then you can give them what Sherry has basically stated earlier, okay? That because of the it's due to arranged of the basically hydrogen atoms. Yes.
I don't think I've ever been on an elevator where somebody's asked me about water.
You are on a bus. How is that? Okay. So try to just give you a scenario where people can wonder about things. Okay.
I would think they were a weirdo if they came up and asked me.
You just want to know, okay? Okay.
And so, do you want this answer as our question too?
Yeah, that's the second question of the day, okay? Because we just answered the question by stating the fact that molecules of water in this case are sticky, okay? And my question is, why are they so? And the answer to it is because in this case, they have this property, which is the molecular polarity, okay? Some molecules do, others don't, okay? Water does, okay? And like I said, if somebody is curious enough to ask you more details, you can give them the details they want. Yes? Okay, very good. Okay. So ion dipole interaction is also possible. The attraction between an ion and dipole, example, in the case, for example, when you take sodium chloride, which is salt, and you put it in water, Then in this case, you have water, which is a dipolar structure, which has this polarity that we just mentioned, and sodium now, which is ions of sodium and ions of chlorine, basically floating in water. Now the ions themselves, they will interact. If it's a sodium, it's going to be attracted to the oxygen part of the dipole. If it's a chlorine, which is negatively charged, it's going to be attracted to the hydrogen side of the chlorine, of the water, I'm sorry, okay? So that's basically how you can think about it. So in this case, the sodium will be facing the oxygen part of the water because the water itself has this dipolar structure, whereas the chlorine has this negative charge because it's an ion. In this case, it's going to be attracted toward the hydrogen part of it. Okay, so if you ever dissolve salt in the, if you ever put salt in water, this is what's going on inside of it. Okay. Whereas dipole to dipole interactions is what we just described, basically. In this case, I have a dipole, which is really a hydrogen with positively charged, basically, side, and the oxygen with a negatively charged side. And in this case, the oxygen and the hydrogen can form a bond, in this case, due to this dipolar interactions, this polarity. Again, there is another possibility where you can have a dipole to an induced dipole interaction. So in this case, for example, what you have an oxygen molecule in this case that is neutral. It has no polarity whatsoever. It's not polar, non-polar, okay? And you bring it next to an oxygen in this case, and it's going to basically induce a dipole in the oxygen molecule, and that's how actually oxygen dissolves in water. Okay, through this way. It's very, very important process for the living animals inside the water. For example, fish, because fish extracts this oxygen when breathing the water and taking it from this bonding. It's much easier for it to break it through its gills. Takes the oxygen and now breathes the oxygen. So really, fish does not breathe water. It basically takes in water and removes the water part from it and takes the oxygen for its own system, for its living thing. So if you want to, basically, if the water does not do this property, then there could not be marine life, at least under the water, at least in terms of marine life that takes actually oxygen, okay? So that's really a very important process for the living animals inside the underwater. They do that, they take this oxygen. Now, this is not, like I said, the oxygen by itself is non-polar. It has no polarity whatsoever. The water molecule is polar. It's actually a highly polarized molecule. In this case, what happened is going to move the electrons. So the negative side now is facing, the oxygen side is facing the other oxygen. So it moves the charges, basically, because now it's negatively charged. So it's going to repel the charges to the other side. And now the oxygen would look like, the oxygen molecule that is, would look like it's polarized, okay? This is an induced effect, not by, it doesn't occur by itself, okay? Just similar to the experiment that we did when we did the balloon. Basically, if you take a balloon and you rub it through a hair, and now I lost all of my hair, I just had a haircut, so it's not gonna work anyway. It did not work before, even with my little hair I had. So if you rub it through hair and you put it on the wall, it's going to stick. The reason why it sticks is because of the fact that the balloon, which is now charged, has a charge in it, will induce a charge on the wall. That was neutral and continued to be neutral, but charge has shifted a little bit in the wall to basically allow for this bonding to occur. If you wait long enough, that basically will become neutral again and the balloon will fall to the ground. So that is basically the same effect. So it's an induction in this case. It's not directly. Okay. So it's unlike the first one in here, which was dipole to dipole. Both of them are purely polar molecules and they do interact that way. In this case, no, it's actually an induced effect. Okay. That is, like I said, a very important thing in here for fish and other marine life. It depends on this effect, depends on this one. Okay. Here is another question, and this question is already answered in here, but that's a question of the day. Is it possible for fish to drown? And the answer is yes, okay? If you remove the oxygen from the water, or there is very little oxygen in the water. So in this case, yes, it's possible, because then the fish will be starved of oxygen and basically cannot survive, and now it's going to drown. And the only reason we drown underwater is because we are starved from oxygen. We take all of that water for nothing. Okay? So that's the third question. So there was 3 questions. Do I need to type it? Okay, since I promised Sarah I don't want to disappoint her. So why fish can we
Just want to disappoint you.
yeah, okay, can we drown? Can fish drown? What was the question in here? Let me paste it in here just to make sure, okay, that all the bases are covered in here. Is it possible? Oops. I mean, it's a good practice, really, honestly. So it's not. Okay? And you know the answer to it, okay? Yes, of course, we can, if we remove enough oxygen from the water. If there is not enough oxygen in the water. Yes, is everybody on board so far? Okay, very good. So we have 3 questions for the day today. And we have about 15 minutes, I guess, to finish these things in here. So let's. Again, this is, we just answered it. Non-polar materials such as O2 is soluble in polar materials such as water by way of, in this case, dipole and induced dipole attraction. So it's not dipole to dipole. It's not real dipole. That's an induced dipole. Okay. Of course, there is no ions in here. Where is that coming from? It's not like, for example, in the case of salt in the water. That is soluble because of the ion dipole interactions. That is for the case of salt. Regular salt, that is. But in this case, no. It's through dipole-induced dipole interactions. Which brings me to another kind of dipolar interactions due to, I mean, argon, for example, when we mentioned the case of the inert gases, they don't interact. Sometimes they do, and this is one of them, is through a temporary dipole in argon. So that's, for example, due to other processes such as heat and things like that. You can have that possibility, and that could lead to bonding in here and interactions. Okay. Okay, I think we can stop in here. Like I said, I really did not. I wanted to focus really more on the molecules that I said in here for this chapter, because if you guys have this understanding, I will be very happy with it. And that's where the test is going to focus mainly on these things, okay? Especially in terms of the shell structure, the give explanation of a lot of things in terms of the properties and the 2 main chemical bonding for the actually 3. You have the case of the ionic bonding, the covalent bonding, and also now we talked about the dipole and dipole and the dipole induced dipole interactions. Okay, so that is really the key things for this chapter. Okay, so watch for the first of all chapter 16 that is going to be posted hopefully tonight. Okay, ready for Thursday, and also the quizzes that follow. Okay. Any questions? So you have 3 questions today for the day. Okay. Any questions? No? Well, I see you guys Thursday then. And take care. I'm going to stop the recording.
Bye.
Bye.